Okay, the theory is nice, but it's always helpful to work out a complete example using random forest throughout. And so I'm going to work through a complete example and showing you different tricks while we're going through it. Something that I'll mention is that Mike is really good at letting you think for yourselves and opening a space for you to uncover these problems and uncover solutions. I like trying to indoctrinate you as I go through. And so you'll see that throughout. I'm giving you a fair warning right now. So first stage of indoctrination is your first goal should always, always, always be getting a generalized prediction as fast as possible. You shouldn't spend a lot of time trying to tune your model, trying to add features, trying to engineer features until you've actually gotten one prediction at least. The reason why that's a really good thing is because then you'll set a benchmark for yourself and you'll be able to directly see how much effort you put in translates to a better prediction. What you'll find is by working on many, many models, some efforts you put in, some work you put in, actually has very, very little effect on how well your final model is at predicting new observations. Whereas some very easy changes actually have a lot of effect. And so you get better at allocating your time more effectively. Okay, so with that indoctrination or explanation, we could move forward. You'll see first I import Random Forest Regressor, ROC AUC score, which I might call CStat. That's the language you'll use in statistics, not in machine learning. And so you might catch me calling it the CStat and seeing it throughout. But whenever I say CStat, I actually mean ROC or AUC score. Importing pandas, reading in the Titanic data, and then popping off the variable of people who survived as Y. We can then describe this data. You'll remember that the describe method only shows the numeric variable, so I know there are categorical variables in the dataset, but I'm going to skip them for the moment. I do notice that age has missing values, and I know that if I were to run any estimator or any machine learning model in scikit-learn that has random data or that has missing values, it will not run. And so I know if I'm going to use age, I better fix that really fast. And so that's what this is doing. I will just impute age with the mean and then describe the data again to make sure it's correct. So sure enough, age now has 891 correct values, or at least filled non-missing values. Next, I'm going to do this fancy code just to get the numeric variables and to look at the numbers associated with the numeric variables, because my strategy for building a very, very fast model, as fast as possible, is to start by ignoring all of the categorical variables. Now something you'll notice is p-class, this is a categorical variable, but there are only a few options. There's 1 or 2 or 3, and so if we think of our decision tree, well, there's only so many ways you could split that data. You could have 1, you could have 1 and 2, or you could have 3. Or 3 and 2. Those are the only possible ways you could split this data. And 1 and 3. I guess that's another way. But Random Forest handle that automatically for you. So I don't even have to do anything else for p-class. I'll just use that right away. Also, I noticed that passenger ID is just numbers. 1, 2, 3, 4, 5. It looks like a worthless variable, but I'm going to leave it in for a few reasons. Like what I mentioned here, I don't want to go through the effort of dropping it. And secondly, there's always a sneaking suspicion that some of these variables might be valuable. So for example, if these numbers weren't assigned randomly to passengers, it might be true that passengers who have earlier numbers, maybe they purchased the tickets earlier, and maybe there's something special about that, and that might be predictive. So I'll leave it in for right now, and it won't harm anything, because if it is worthless, a random forest will just ignore it. Let's build our first model. You'll see that I do a few things. This is in all my models. I usually set a few variables always the same. So number of estimators I set to 100 to start, because I know this is a small data set, so this will run very fast. Out of bag scores I put as true. This lets us capture that really neat validation technique, and I'll show you how to use it in a second. And then for you all, I set a random state equal to 42, so you'll be able to replicate these results. Now what you'll see is when I fit the data, I'm only selecting the numeric variables. So it's training a model just on the numeric variables, ignoring all the categorical variables. And then when the model is trained, I get access to this attribute, out of bag score, with a trailing underscore. This trailing underscore, all the methods that have a trailing underscore are available after the model has been trained. So you'll see a lot of methods with trailing underscores, like base estimator, feature importances actually has a trailing underscore, number of features, number of outputs, out of bag score. All of these are available only after you've run a fit method. What this out of bag score produces, because this is Randomforest regressor, is it produces the R square value. We want to use the C stat. We want to calculate the C stat. So here's how we do it. We simply create a new variable, y out of bag is equal to model dot out of bag prediction, and there's an underscore there. And so I'm going to run this and insert a new cell. So what we see is the C stat of this is 0.738, which is a pretty good benchmark. It's respectable. It's not the best considering it's on the Titanic data set, and we could do better than that. But it provides a benchmark, and what you could see is we got to that benchmark very fast. This was a very rapid where we imported the data right here, described it a few times, imputed age, just picked numeric variables, and then trained the model and got this 0.73 C stat. So we have this benchmark, and before I go forward, I want to show you all what y out of bag, what this looks like. It's just an array where every single observation has a prediction, the probability of survival. And so these are the out of bag predictions. We're just using those in the ROC score to get the C stat. So we have a benchmark. Now let's make some improvements to it. Let's make some changes. First, to the data set, we'll add these categorical variables in. Here's a function you all might want to save. You'll remember that when we're describing the data set up here, it only uses numeric variables. This function right here does descriptive statistics on just the categorical variables. And so it lets us see that, okay, for name, they're all unique. For sex, there's only 2 values there. For ticket, there's a lot of unique tickets. For cabin, a lot of unique cabins. And for embarked, only 3 values there. So from this, there's some of the variables that I don't want to deal with. So like name, I'm sure there's great signal in some of the names there, or some of the tickets might have something unique, or passenger ID, that might have been unique too. I decided just to drop it all of those variables, and only deal with the other ones. So what that leaves is it leaves cabin. I noticed that there's a letter at the beginning of each cabin, and I don't know what that means for this data set, but I have a suspicion that it might be valuable. So what this code does is it's a simple apply function that takes every single observation in the cabin variable. It runs the observation through this function. If the reason I have this try and except is because there's missing data there. If there's no missing data, it's just going to return the first letter of whatever that value is of that particular observation. Otherwise, it's going to return the word none. And so essentially what I've done, or what this does, I could show you x.cabin. Here's what it transforms the data to look like, where you have the word none if it was missing, or C if that was the initial letter of your data set. Okay, next we have this fancy loop, and what this fancy loop does is it goes through these 3 categorical variables, sex, cabin, and embarked. The first step of the loop is to replace all the NaN values with the word missing, so it's almost as if there's another class that's named missing in your variable. Then I use this very nice function in pandas to get all of the dummy variables for that categorical variable. I concatenate the original data frame with these dummy variables, and then I drop the original variable, the original categorical variable. Next, if I were just to go here and print x, what we see is, there's our data, and it looks very nice. Except there's a problem. Actually, let me see, it doesn't look like there's a problem here. We have the settings on, so it looks good. So all the columns are showing here. What you might find in your work is you might find that what the IPython notebook does automatically is it'll hide some columns. It'll compress it to make it smaller. And that could be problematic. So I wrote this little simple function here that ensures that there is no compression in the columns. It shows them all, and it's guaranteed to show them all. When we're looking at these columns, we find that there are some columns that might be worthless, but we could keep them. This one we actually cleaned it up, so that's not an issue anymore. But now that we have this data set, with all of these columns, we could build a model on it. And here's the model. We'll just say model equals random forest regressor with 100 trees with out-of-bag scores being calculated throughout it, using all the processors and having a random state set to 42. So let's run it with all of the data, and we get a 0.86. So that's very good. That's a pretty good model. Now before we try some different parameters from the model, you'll remember Random Forest Regressor has many options in it that we could choose, and there are 3 that I said are very important when we're trying to make the model better. Let's use a random forest to help us with some exploratory data analysis. Excellent, so we're going to use a random forest model to help us with some exploratory data analysis. Namely, we could use it to calculate which variables are important in the model. So by accessing this features importance attribute of the model, we could print out which variables are important numerically. So this isn't very helpful. First of all, it's hard to understand this in scientific notation. And secondly, it corresponds in order to the column names. So P class would be this 0th element in this array, and then whatever's next, age, would be the 1 position element in the array, and so on. And so it's not that helpful trying to just look at this array. So what we could do is we could do some very, very simple code to say features importance variable is equal to pd.series. So we're going to make a series where the data in the series are these feature importances, and the name or the index of the series is in the name of the columns, just in order. And so by running this code, by sorting these variables and then by plotting it, we get a very slick bar chart, where this bar chart shows here is what each variable viewed in isolation. Here's how each variable is important. So we could see age is the most important when viewed in isolation. Fair is second most, and sex female is third most, sex male is fourth most, and so on. And you see all these cabin names. Each one is a little bit important. But what we find is we see repeats. So notice how embarked, each one of these is 3 different bars, and cabin, each one of these is many different bars, and sex is 2 different bars. So we might want to see an aggregate view. So what's the power of the entire feature, the entire variable, viewed by itself? We could do that using this very slick function Mike wrote. So complex function, but all you have to know is this part, where I just put in the model x.columns, and then summarize columns equals categorical variables. And when I run this, I get this chart. And what it shows is sex is the most important variable in this data set, followed by age, followed by fair, followed by P class, and so on. And so we get a very, very nice summary to see which variables tend to be important and which ones are not. So we see here the most important variables. And in practice, when you have very, very large data sets with hundreds and hundreds or thousands of variables, this is a good idea to run EDA, find which variables are most important for prediction, and if your goal is prediction, only select those variables for your final predictive model. What you'll find is the accuracy of your model actually might improve, and your model will run much, much faster and be faster to train. Okay, next let's optimize the parameters. So we've done some EDA, we've optimized some other things. Let's do some parameter tests. And so you'll remember here are the parameters that I said you should optimize. Two of them that are not listed that I removed because we've already talked about are the random state parameter and the out-of-bag score parameter. So we'll cover all of these other parameters, and let's start with the parameter that makes it easier to train your model, which is InJobs. So what I'll do here is I'm going to run two cells. One is going to be timing how long it takes to train a model where InJobs is equal to 1, and another where InJobs is equal to -1. And what we see is, actually something good to point out here is this %time_it function is another great feature of the IPython notebook, where if you put that as the first line in a cell, it's going to run this cell several loops and then find the best speed of each iteration. And so technically how you'd interpret it is it ran one loop where it ran the code 3 times, and then the fastest time of those 3 times was 2 seconds. And then the other one, when we had InJobs equals -1, the fastest time is 1.3 seconds. So we see that there was a slight performance gain. What you'll find is as you have faster and faster computers with more and more cores, this performance gain will be more dramatic. Okay, now let's try to optimize for these 3 parameters that will make your model better. Now there are official grid search algorithms in scikit-learn that you could use, but I'm just going to do a very simple way. This is almost like a custom grid search method, where we will iterate for each one of these parameters, number of estimators, through what if we build a random forest with 30 trees, 50 trees, 100, 200, and so on, and each time printing out the C-stat, or the ROC-AUC curve. And so here's what we find. I had each one of these run, and then it prints a line chart that shows a plot of the accuracy. So we see with 30 trees, it's 0.85, and then you get to 0.86 with 50 trees, and you're stable about 0.86. And when we look at the chart, you see this slight inflection point. This does not mean that it's going to keep going down in the future after 2,000, 4,000, 5,000 trees. And instead, you'll see it sort of staying around, hovering around this spot here in this line. So what this tells me is that at about 1,000 trees, you're pretty much as high as you'll get with this random forest model. There's not a lot of reason to train it with 100,000 trees. It's pretty flat after 1,000. Next, we could try different max features. So you'll remember max features are the number of variables it considers at each split point. A rule of thumb is for regression tasks, when you're trying to predict a value, a numeric value, it's good just to use all your variables at every single split point. So you're not really using a random forest. Instead, this would be considered a bagging method, and that's what you'll see in the literature. They used bagging to make a prediction, but it's still, you could still access it in this random forest class. So for regression tasks, the rule of thumb is just use all of the variables at each split. For classification tasks, if this was a classification task we were doing, the rule of thumb is to use the square root of 2. Or excuse me, the square root of the number of features you have, variables. So if you have 100 variables in your model, use 10 at each split. Now this task right here is a binary prediction task, predicting 0 or 1, but because we're outputting a probability, it's still sort of like numeric. We're producing a number between 0 and 1. And so what we will probably find is the auto, which for this auto is also equal to none, which is also equal to just use all of the variables at every single split. That's probably going to perform better than square root, log 2, using 90% of your variables, using 20% of your variables, all of those options. So we will run this code, and let's see what happens. So auto and none produce exactly the same number because they're exactly identical. They're using every single variable at each split. These other variables present different numbers. I put it in a bar chart this time because there's categorical labels. And what we could see is which ones are the furthest to the right, which ones have the highest C-stat, auto and none. So that's the default setting. All of these other ones are lower. One that's a little close to it is this 0.9, but that's just because it's almost using all of the variables anyway. So we might as well use all of the variables. So then our very final thing we're going to test is the minimum samples per leaf. So you'll remember that when you're training a decision tree, you'll keep splitting each node until you only have one observation left in each node. So you split 2 observations, one goes to one side, one goes to the other, and you're done. You've run out of data. You can't split any further. Well, what you could define is you could say, actually, let's stop training it before you get just to one observation in each terminal node in your decision tree. So what this is going to do is it's going to train the model with one or the minimum samples per leaf option equal to 1, and then train it equal to 2 and 3 and 4 and 5 and so on, all the way to 10, and we're going to see how varying the number of observations in the final node changes the accuracy of the model. And here we go. We get this beautiful curve that shows that right at about 5, so if you continue to split your data until you have 5 samples in each node, in each end node, you tend to maximize your data. You maximize your C-stat. So right here at 5, we could see you have a C-stat of 0.87. So we got extra lift out of it. So from all of these optimizations, we find a final model where there's 1,000 estimators in the model. The out-of-bag score is on. There's the in-job is -1, random state 42. We're using auto to determine the max features, which is just every single feature. Every single variable is considered at each split. And we're stopping splitting a node when there's 5 samples in that node. Fitting this data, and we're getting a final C-stat of 0.87. Now, I know Mike has gotten a higher C-stat than that, but that required some extra feature engineering and looking at this data more in depth. Once you run through this and once you optimize your model, the next best place to go is feature engineering. That's how you get that final performance gain. And so that means really getting familiar with your data, being creative with your data, and trying new things and testing it against the benchmark continually. So these are random forests. I hope that you'll be able to use this tool set and this tool in the future. I found it very valuable in my work, and I'm sure you'll find it valuable in your studies and in your work in the future. Thank you.